Hello students, welcome all. So in today's session we are going to start wave optics. So we have completed ray optics and it's quite a big chapter. Lot of things are there, but we have tried to go through each and every aspects, each and every topic of this, right? But of course we will be solving a lot of questions. So we will be going today in the new topic, next topic, which is uh, the wave optics. So yes, Lalit. So we are going to start today wave optics. Okay. So let us start wave optics. Wave optics. Wave optics. Wave optics. So this chapter uh, is different from ray optics. How? Because in the ray optics, we were considering different phenomena. What are those phenomena? Reflection, refraction, dispersion, right? And all those phenomena where total internal reflection, all that where we are taking the light going in a straight line path, right? But in this chapter, we are going to deal with the wave nature of light. Wave nature means light will combine, two light waves can combine and produce interference or superposition, right? So somewhere intensity will be more, somewhere intensity will be less, like that. No? So many concepts will be there in this chapter. It's a very important chapter. So let us start this chapter without much delay in that. Okay, so let's start. So wave optics. So first of all, what is the scope? We'll understand the scope of wave optics. Scope of wave optics. That means where can you apply the concept of wave optics? That means in case of light, where can you apply the concept of wave optics? So suppose for example that there is an object with which light is interacting. This object can be anything. This is an object. This is the object and light is interacting with this. This is light, right? Light is interacting with this object, and let us consider that the size of this object is a, and light has wavelength lambda. Lambda is wavelength. So if wavelength wavelength is much smaller than the size of the object, in that case we consider only the ray optics phenomena which we have discussed previously, right? So if you consider the wavelength of light to be much smaller as compared to the size of this object, then the the optics phenomena, ray optics phenomena is prevalent. Is prevalent. Prevalent means it is more, more dominant, more dominant. It doesn't mean this we cannot explain the phenomena using wave concept. We can explain that, but ray optics phenomena will be more useful in explaining that, you know uh, process. In order to explain this phenomena, if the wavelength of light is much smaller, but if wavelength of light, if wavelength is comparable comparable to a, then then wave phenomena or wave optics phenomena wave optics phenomena is more prevalent. More, here also you can say more. It is prevalent, but it is more prevalent. More prevalent. Okay. Right. So this is the scope of ray optics and wave optics. So if the wavelength is comparable to a, comparable to size of object, object can be anything. As I told, object can be anything. It can be lens, it can be mirror, it can be prism, it can be small opening or a hole or a diffraction gratings. It can be anything. So if the wavelength of this light is going to be comparable means not that much small as compared to the first case. Suppose wavelength I talk in nanometer, right? And size I take in meters or centimeters. Then you have to go for ray optics, reflection, all that. But if you are saying that wavelength is in nanometer and size is also in millimeter or micrometer, then definitely you will go for wave optics phenomena, and that is why we are going to study this chapter. Okay, so wave optics phenomena we will be discussing many important things, starting with interference, diffraction, and all that. Right, so let us start this chapter. So there are many concepts of waves which you have studied in grade 11. Same concept of wave will be coming here in this chapter. Okay, so let us start. This is the introductory part. Now we are going to start about the wave theory of light. Wave theory of light by Christian Huygens. Christian Huygens. Okay. So Christian Huygens, he gave the wave model of light. He explained the behavior of light by considering it as a wave. Okay. So I'm not going to more detail of all that theory, but some important points I will try to mention that. Okay. Some important points. Yes. Yes, Sam. You're not able to see me. Lalit, can you see me? Sam, I think you just check your network. Okay, so wave theory of light. What are the wave theory? I will try to write some important points. Otherwise, it will not be so much informative. Let me cover the points also. Let me refer to textbook also. I think before going into the wave theory, let me go before wave theory. Let me cover about the Newton's corpuscular theory. Okay, Newton's corpuscular theory. Newton Newton's corpuscular theory. Newton's corpuscular theory of light. I will write all the important points. Okay. So first thing is that Newton. See, Newton was a genius person. He worked on mechanics. He given so many ideas about light, and he was a great mathematician also. Right. So he have started studying about light and its nature, and he gave this theory to explain the behavior of light. Okay, so corpuscle means particle. Okay, so it's a particle model of light, and Newton have gave, but due to some reason, Newton made some assumptions due to which his theory failed. But I'll tell you, actually didn't fail it, but it became more successful afterward. But people, although they are not saying it's Newton law, but later Einstein figured out that light is made up of particles, which Newton gave the first itself. Newton tried to give the idea of light as a particle. Okay, and let us see what are the important points in that. Okay, so first point, Newton thought that light is made up of tiny tiny light light means massless and elastic particles elastic particles called called corpuscles corpuscles. Okay, which are emitted which are emitted by luminous bodies luminous bodies luminous bodies. So what are luminous bodies? Luminous bodies means which emit lights. which emits light. For example, electric bulb, tube lights, or naturally, like for example, sun or moon, any objects which emits its light, that is called luminous objects. So such luminous objects are emitting corpuscles, right? So that is the particle of light, and these particles are tiny, very very small. Light means massless. The concept of massless itself is very difficult to understand. Elastic particles means they have elastic collision. Whenever they will collide, there is no loss of energy. But the concept of massless was a very, very important assumption which Newton made in his theory. Okay, let us write the next point. So the next point is corpuscles travel with the speed of light in all directions. The corpuscles travel with the speed of light in all directions, in straight lines. For example, suppose this is a source. This is a source of a light, electric bulb or anything. Source. From this source, the corpuscles will be going in all different directions. Means all possible direction it will be going. All possible, whatever possible direction you can think of, it will be going. These are small particles of light, which are called corpuscles. That is the Newton's idea. It's a theory, means we cannot see them, but we can try to make some imaginations, right? And that's what is the imagination corpuscles. Okay. Then next, third point. And each of these points are moving with the speed of light. Speed of light. Speed of light means 3 into 10. In vacuum, if you consider 3 into 10 to the power 8 meter per second in vacuum. In vacuum. Right? Okay, what else? What's more? Corpuscles carry energy with them. When they strike the retina of eye, they produce senses of vision. Corpuscles, corpuscles carry energy with them, and when they hit retina, and when they hit retina, they produce sensation of vision. Sensation of vision. So then next point, right? Next point. Corpuscles of different color are of different sizes. Corpuscles of different colors are of different sizes. Okay. For example, if you compare red corpuscles are larger in size than blue corpuscles. So red color light, the corpuscles or the particles of red color light, they are larger than blue color light. Okay. Then point number 5. The corpuscles carry energy and momentum, carry energy and momentum, and travels in a straight line This fact can be used to demonstrate demonstrate the propagation, the rectilinear propagation of light, propagation of light, rectilinear propagation of light. Then what is law of reflection? Law of reflection and law of refraction. Law of reflection. So using this theory, Newton can very easily explain these things. But there is a but now. What happened then? Why his theory failed? But point number six. Point number six you can write. The corpuscle theory, the corpuscles, corpuscles travel travel faster in air, sorry, faster in water than in air. But the corpuscles travel faster in water than in air. This point was experimentally proven wrong. This was proven wrong. Okay. So this is a major point where Newton's law means Newton's theory, not law, theory. If corpuscles travel faster in water than in air, this is a theory which he made, and this theory was proven wrong experimentally. Experimentally, it was proven wrong, so people rejected his idea. Okay, people rejected his idea, and what else he could explain with his theory? He could explain something. What are those? Already I told. He could explain rectilinear propagation, law of reflection, law of reflection. But his theory, of course, this was a wrong thing which was happened. But his theory could also fail to explain. His theory, his theory failed to explain some of the important things of light. First, interference, interference, diffraction, diffraction, polarization, polarization. Okay, these three phenomena could not be explained by Newton's corpuscular. Okay, we can say Newton's corpuscular theory can explain these things, but this it cannot explain, and also it could not explain this experimental observation, because according to experiments done, the speed of light travels faster in air than in water. That's why his theory went wrong. So people rejected his idea. But let me tell you, this theory was one of the means biggest idea of that time, because later Einstein proved that light is made up of massless particle which is called photon, and for that he got Nobel Prize. Or photoelectric effect, explaining photoelectric effect only, he got Nobel Prize. So basically Newton idea was correct, but he was trying to apply the concept of classical mechanics in this corpuscle. Actually, this corpuscular model or corpuscle is same as photon only, but Newton could not get that idea that how that can happen, right? So, but temporarily you can say that his theory was not accepted by people, right? At that time. So, because that time the wave idea was coming into more into picture, because at that time sound wave was being studied at that time, and people believe that sound wave requires medium for propagation, and sound wave is a kind of vibration that happens in a medium, and that vibration or disturbance travels in that medium. All those blah blah, those theory people believe that. And the same way they try to explain light in the same manner as that of sound. So Christian Huygens tried to explain the light based on the same idea of sound. Okay, because that time people were studying sound as a wave, so he tried to borrow that idea and apply in the concept of light, and he could also successfully explain many things like these phenomena. So these phenomena, particularly these phenomena, are related to waves. They are related to waves because they are wave phenomena. So that's why it cannot be explained by considering light as a particle. Definitely it cannot be explained. Okay. So now we will go into the Christian Huygens means wave theory. Let us go into that wave theory. Okay. Let us go into that wave theory. Now we will go into the wave theory, and in this theory, let us write important points also. If we don't write important points, it will not be useful. So let us write this point. Okay. According to this theory, luminous body is a source of is a source of is a source of disturbance is a source of disturbance in a hypothetical medium called ether. Okay, ether ether pervades all space. That's a very interesting idea. So what was this idea given by Huygens? He gave that any luminous object means anything which emits light. Okay, that object um, disturbs the medium around it. So then you can ask, what is the medium? Suppose in space, if you take, there is no medium. How can light travel in space? But now he brings the idea of medium. He says that even in space where you say there is no medium, there is a medium called ether. Okay. He says that there is a medium already existing everywhere. Already existing, there is a medium, it is already existing, it is existing everywhere. Inside the sun also it is existing. Everywhere such a medium is existing, that he is calling as ether. It is not the chemical ether. By the way, in chemistry, you must have studied about ether, right? This is not that ether. This is a name of the medium which is existing everywhere, he is saying. And he says that this medium is present everywhere. Wherever you can think, wherever you cannot think, everywhere this medium is present. And if there is a object which emits light or luminous object, that will disturb that medium, and because of the disturbance of that medium, light will travel as a wave. So he is applying the concept of sound actually, because that time people were understanding about sound waves. So he is borrowing that concept of sound waves, and he is applying the concept of sound in this slide. Okay, so that's how he is bringing this concept here. Second point, let us note about the second point. Second point, he is saying that it is assumed to be transparent and having zero inertia. This ether is assumed assumed to be transparent and having zero inertia having zero inertia okay, zero inertia. The disturbance the disturbance from the source is propagated is propagated in the form of in the form of waves through the space. Okay, so in that medium, what happened is that medium also property he's highlighting that medium has zero inertia and medium is transparent because people will ask him question. People will ask him question that you are saying that ether is there and what is the visibility of that. For example, suppose if I say water is there, so by looking at water you can understand water is little bit transparent. If you see, look at glass may also be transparent, but some medium, like for example oil, if you take it may not be transparent, and some medium may be opaque, it will not allow light to pass. So what kind of transparency that medium ether has? So he is before itself putting this point in his theory that it is completely transparent. I mean, suppose I am able to see you, you are able to see many things. So in between us there is a medium, even if there is a space, let us say there is no air, right? But still that medium ether is there, it is completely transparent. Actually everything is present in that medium, so it is existing everywhere, right? So that is the idea he's putting, and he's saying that the disturbance, which is nothing but the wave, that disturbance travels in this medium in the form of wave. This is exactly the same idea of sound, because suppose for example a string you vibrate, that disturbance travel in that string. Or if you produce sound wave, so sound wave travel in air. So exactly same idea he's bringing here. Okay, that means he's trying to consider exactly like a light wave, exactly like a sound. Let us try to know the third point. Third point. The waves carry energy and momentum. The waves carry energy and momentum. Energy and momentum. That's what it does. Now here very important thing is that Huygens assumes Huygens assumed that light waves were longitudinal. So he believed or he assumed that it is longitudinal, and that is where he made a mistake. Already I told that because he was comparing it with sound. So he believed or he assumed that light waves are longitudinal, and that's where he made mistake. Okay. And that is of course one point of his limitation, but you can also write some more points that uh, when polarization was discovered, then to explain light were assumed to be transverse in nature by Fresnel. Okay, note that when when polarization when polarization phenomena when polarization phenomena were discovered, light was considered as transverse wave transverse wave to explain polarization by Fresnel. Fresnel was another scientist. So Fresnel had to explain the polarization. For explaining polarization, Fresnel had to believe or he has to assume that it is a transverse wave. And now this is completely contradictory. Huygens says it is longitudinal, Fresnel said it is transverse. So there was a contradiction. That means Huygens theory, longitudinal wave cannot be used to explain polarization. That's what it is. Okay. We cannot explain polarization using this theory. Okay, let us write some pros and cons in this theory. Huygens wave theory, pros and cons. Pros and cons. Pros and cons means some advantage, some disadvantage, but mostly it was accepted. This theory was a good theory, so mostly it was accepted. So let us note first wave theory, or this theory explain successfully, successfully. What are the things it can explain successfully? Note that it can explain interference, interference. It can explain diffraction, diffraction. These two phenomena it can explain successfully. Also, it can explain the propagation of light, propagation of light. All these phenomena can be explained. Reflection, reflection also can be explained. Reflection, refraction. All these phenomena was explained by this theory. So this theory was highly successful model. Okay, this is the pros. What is the cons? Okay, Huygens theory, Huygens theory fails to explain, fails to explain first thing, photoelectric effect, photoelectric effect. Then second thing, Compton's effect, Compton's effect. Okay, and how he is successfully able to explain these things? He introduces a concept of wave front. Wave front, a concept, a concept of wave introduced by Huygens. Huygens introduced the concept of wavefront, and using the concept of wavefront, he could explain everything, almost everything he could explain. But he could not explain the photoelectric effect because those phenomena required particle behavior of light. Okay, these phenomena are related with particle nature of light. Particle nature of light. And these phenomena are related with wave nature. Wave nature. So light has dual nature. Light can behave as a wave as well as particle, right? Light behaves in different ways, in different circumstances. Okay, so that's why the next chapter to this is the dual nature of radiation and matter. Next chapter you will be seeing that. Okay, but anyway, here you should know that light can behave in both ways. It can behave as a wave as well as particles. Okay? Right, so that's how we are going to start now with the wavefront and try to explain many concepts using this. Okay, so let us start this wavefront concept, and then we will learn very important things with that. Wavefront. What is wavefront? Wavefront, it is the locus, it is the locus of all points vibrating, vibrating in the same phase, in the same phase. Suppose, for example, that there is a source of light, and this source is emitting light radiations, right? So it is disturbing the particles around it. Okay, so all those points which are vibrating in the same phase. They are, after joining those points, you will get a surface. That surface is called wavefront. Locus of all points means joining all those points which are vibrating in same phase. So now which point will vibrate with same phase? Try to understand. Suppose I create a disturbance here. I create a disturbance here. All those points which are equidistant from this source, they will vibrate same time in the same manner, right? So for example, suppose if this particle is here and some distance r, same distance r this another particle is there, because wave will be reaching to these points in the same time, right? Suppose light waves are created, disturbance is created, disturbance will reach from source to point 1 and point 2 in the same time, so they will start vibrating in the same manner. So they will be in the same phase. So try to join all those points which are at the same distance or equidistance from this. So when we join all these points which are equidistant from it, you will get a sphere. You will get a sphere. So this is called spherical wave front. Spherical wave front. Okay. So what are spherical wave fronts? Those points which are equidistant from the source, they are vibrating in the same phase. So by joining all those points, you get a surface, of course, in 3 dimensions. This surface is representing a wave front. Not only this, there are many wave front will be there, because there can be many spheres you can make, right? Now, Hagen explains how actually waves travel in space. So, this source, this is a source of light, and this source of light has produced this wave front. Okay. Now, each point on this wave front, is going to behave as a source of light. I am showing some few points here on this surface. So each point is going to behave as a source, means they will produce their own wavefront. So each will produce its own wavefront. Let us say it produces its wavefront. This will also produce its wavefront. This will also produce its wavefront. This will also produce wavefront. Like that, they will be producing wavefront. Okay. These wavefronts are called secondary wavelets. These are called secondary secondary wavelets. Wavelets. Okay. And each point on this spherical wavefront is behaving like a secondary source. So they are producing secondary wavelets. Now, if you try to combine these secondary wavelets, if you try to make a tangent surface by joining this, try to make a tangent like this. This will be the next wave front. This will be the next wave front. Next, next wave front. Next wave front. So you can clearly see that from each of these points, of first wave front, another secondary wavelets come, and by joining all the secondary wavelets, you got the next wave front. So like this is happening, okay? Like this it is happening. That's how the light is going to travel from that source to this way. It is keep on traveling, okay? So from that source, light is traveling in this way, and size of the radius of the wavefronts will keep on increasing. You can see that. So what about the rays? Rays will be traveling like this way. Okay, note that rays will be traveling like this way in the radial direction. Ray of light will be traveling in radial direction. Okay, so this is nothing but the ray. The ray is traveling in this direction. Note that ray is always perpendicular to wavefront. Any wavefront you take, the ray is always perpendicular to the wavefront. Yes. So this is how the ray will travel from the source, and we are taking a point source. Remember here, the source is a point source. This source will emit wavefront, and each point on that wavefront will behave like a source, secondary source, and they will produce secondary wavelets. And then by combining the secondary wavelets by a surface, we get the next wavefront, and in that same manner it will propagate. That's how the wavefronts are propagating in this space. Are you understanding this? Yes. Okay, so that's how this wavefront theory concept is very, very important. It is able to explain many, many things. And now we are going to see how wavefronts will interact, how the wavefront will interact. But before that, we should know all the different types of wavefronts. Okay, so right now we have discussed about a spherical wavefront which is emitted by a point source. Okay, point. So you can clearly see that this, as you go away from the source, this radius of the wavefront is increasing, and when you are standing at infinite distance, this radius become infinity. Infinite radius means it will become a plane wavefront. That's what you have to note. Okay, so this is a spherical wavefront, but if you go very, very far away from the source, suppose this is the source, okay, and you know the wavefront are going like this way, no? Wavefronts are spherical, big, 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 like this. You see, as you go away from it, this radius increases, and let us consider that you are standing at very, very large distance, infinite distance. Then here, this is almost like a plane wavefront. You can say it's like a plane. This is called plane wavefront. Plane wavefront. So near a point source, there will be a spherical wavefront. At infinite distance from point source, it is a plane wavefront. Okay. Two type of wavefront we have discussed, right? Now let us discuss about cylindrical wavefront. Cylindrical wavefront. Then we'll come back to each of the wavefront and we'll understand what it is. What is cylindrical wavefront? Cylindrical wavefront means WF wavefront. Suppose this is a line source of light, line source of light. Line source of light means it is emitting light, but it's just like a tube light, very, very thin tube light. You can assume that very, very thin tube light. Then if you try to make a wavefront means all points which are equidistant from this. You can construct a what? You can construct a cylinder. We can construct a cylinder assuming that this is very long, you know, this is very long like this. Assume that this line source is very long. So construct a cylinder, and now this cylinder represents cylindrical wavefront. Cylindrical wavefront. Okay. Now each point on this cylinder will behave like a secondary source. So let us take this point, this point, this point, this point, this point. So many points, you know, is going to behave as a secondary, right? Secondary source. So they will produce what? They will produce small spherical wavefronts, right? They will produce small spherical wavefront. They will start producing small spherical wavefront. Okay. So now when you join these wavefronts by again a similar surface, right? So you will be producing the next wavefront like this. So this cylinder, which was initially a small cylinder, I can highlight that cylinder like this. Previously, this was a small cylinder. Now this cylinder has become bigger cylinder, and gradually the cylinder will keep on growing larger and larger. Okay, so then it will become little more large like this. It will go. Okay, so that's how the cylindrical wavefront will propagate in space. The cylindrical wavefront will propagate in space like this, and this wavefront will be perpendicular to the surface of that cylinder. So this is the ray diagram, the ray of light. Okay, and it will go in all directions. Don't think it is going radially. Okay, try to understand that. Radially means if I draw a circle here, if I draw a circle here, it is going radially. Try to imagine that, because it's a cylinder. It is not just a one-dimensional figure. Cylinder, oh, sorry, it is a three-dimensional figure, right? It is going radially in all directions. It is just like in Gauss law. You remember? Now I think the better analogy is to give Gauss law. Gauss law, you remember a thin wire which is uniformly charged. Electric field goes everywhere in that plane in two dimensions. It's like the same way you can consider this ray as electric field lines going away from the axis of that. Okay, it's like the same manner. Okay, so that's how we can define everything. Now, the important thing about wave is we can try to understand like spherical and plane wavefront and this cylindrical wavefront, the amplitude of the wave and intensity of wave calculation. Okay, let us note that. So let us take the first as spherical. Let us take a spherical wavefront. Spherical wavefront. Second, take plane wavefront. Third, take cylindrical wavefront. Cylindrical wavefront. And in each case, we try to find out the amplitude and intensity because they will ask these questions. Okay. So suppose that there is a point source S. It produces a wavefront like this. Okay. So let us take a distance r from here. We have taken r is the radius of this wavefront. Now, what is the intensity? You remember intensity formula? Intensity. For a wave, intensity is proportional to amplitude square and frequency square. But let us say frequency is not changing. Let us consider frequency constant. A refers to amplitude. A refers to amplitude. You remember in grade 11 you have studied. So intensity is proportional to amplitude square. Okay, amplitude square and this energy which is traveling here, it is falling over this surface, right? So intensity is proportional to this area also. Intensity is proportional to this area. Okay, note that intensity is proportional to um, energy per second per unit area. So inversely proportional to this area because all energy will be receiving here, right? So you know intensity defined as power by area. That is a better definition. Intensity is equal to power by area. Power by area. Power is constant because this source have a constant power. Let us say that it has some power. Okay. So now we can say that both are intensities. So intensity is proportional to amplitude square and power by area. So let us write that amplitude. If you consider power as constant, then intensity can be written as proportional to inversely proportional to area. Area of this sphere is 4 pi r square, so it is inversely proportional to r square because 4 pi is constant. So from here you can say that this intensity is proportional to a square and intensity is also proportional to 1 by r square. So a square is proportional to 1 by r square or a is proportional to 1 by r. This is all about spherical wavefront. So spherical wavefront, you should note about this point. Okay. Then uh, let us move to plane wavefront. So plane wavefront already I indicated. If the source is very away. So this is the plane wavefront. Now from a plane wavefront, you are going at a distance of r. You know that source is infinity, so here also you have to consider a plane surface only. Here also you need to consider a plane surface. Okay. So some distance r you have taken, right? So from here to here, when you're considering this intensity or you're considering the amplitude, so nothing changes when you go from here to here. Note that intensity intensity is proportional to r power 0. There is no change of intensity and there is no change of amplitude. So here the amplitude or intensity are same at both the places. Okay, it doesn't depend on that. Intensity proportional to, it is not proportional to, if you want you may write it is proportional to a square, but remember that this formula of amplitude square is always correct. Okay, but When you go from here to here, the amplitude of vibration does not change. So you can say that this is proportional to r power 0 means amplitude remains constant. Amplitude remains constant. Amplitude doesn't change. Okay. Then what about this spherical wavefront? Spherical wavefront. This is the axis of that, and you have taken a distance of r from here. Now note that the energy is propagating such that it is spread over this cylindrical surface. Okay. So here when you take the definition of intensity is proportional to amplitude square, that you cannot change because that comes from the wave phenomenon. Wave. But what about distance? So here intensity power divided by area. Area you will take here as, let us say this length is L. So surface area is 2 pi r into L. You have to take length. Let us take constant. So a square is proportional to 1 by r. So a is proportional to r power minus r, right? Because take root and bring about, right? So that's how intensity related for intensity and distance. Sorry, amplitude and distance relationship. Intensity is inversely proportional to r also you can write because 2 pi l is constant. Okay, so that point also you can make here that intensity is, in this case, intensity is inversely proportional to r. Okay, so these are the three main concepts in objective questions. They will ask this, right? And there is a very subtle concept, particularly in case of single slit and double slit experiments. Then we will see people do not know about this in textbook also it is not given, but once I have analyzed that, so in there we have to use this concept. Okay, it's a very important concept. By using this concept only we will understand why it is behaving like that, because in case of slip they behave in a different way, the source is different. So if the source changes from this to that, the formula also will change. Okay, so we will see that. So this is a very important concept. Now we are going to discuss about the interaction. In NCRT this is very briefly mentioned, but it's a very important thing. In advanced also sometimes they have asked question. Definitely NEET also they ask question, and main also they ask question. So interaction of the wavefront, interaction of wavefront with various objects, with various objects. Let us consider various objects. Um, we can start with concave mirror, spherical mirrors, prism, slab, right? All these things we will take that. One by one we will take that. So let us take for example, prism. Let us take first prism. It will be very interesting to take prism. So this is prism. Okay. Now consider parallel rays coming. Let us consider parallel ray of light comes like this. Parallel rays are coming. So when rays are parallel, note that this is the wavefront. Wavefront is perpendicular to this ray, right? This is a ray here. This ray is coming like this, but wavefront, note that wavefront is perpendicular to this. That means this is plane wavefront. Note that this is plane wavefront. This is plane wavefront. Now let us consider this wavefront here as A, B. Point A here, point B here. Note that the point B has touched the prism right now, and point A has still not touched. The wave has to go from point A to here to touch this prism, right? Wave has to travel, wave has to take some time because it is still in air only. So wave has to come from point A to this point. It will take some time. But right now wave has already touched, this lower end of this wavefront has already touched point B. Okay. So wave will travel in this medium from here to here. Let us say while the wave comes from here to here, I'm just drawing a rough diagram here. When the waves comes from, this is the wave diagram, okay, when not ray, okay. Inside you may draw some ray diagram also, but right now we are not discussing ray optics, we are discussing wave optics. So note that. So by the time this wave will come from B2, let us call this as V dash, right? From this point, wave has to travel from a node that this wavefront we are talking about, which is AB. So B comes to B dash. By the time B comes to B dash, this point A will definitely come somewhere here to A dash. Why? You may ask why. You can think about it. Why you think about it? Because see, this wave which is traveling inside this medium, right, it is taking slower, it is going slower, right, it is going slower. You understand, you agree why it is going slower? Because it is a denser medium, right? It is a denser medium. Prism is a denser medium, so it is going slower. It will take some time, and in the same time this disturbance A will come here faster because it is running more distance. It is running in this air. It is traveling less distance in air, that you have to understand. It is traveling less distance in air here, so it is traveling more distance in more distance, more time. It is traveling more time in air, so definitely this will be reaching here. So by the time this wave front comes here to here, it becomes inclined. You see, wave front has turned like this. So that is what is happening here. The wave front is turning like this, and the wave front will be going like this now, like this. Okay. So now you can say that the ray of light, if you draw, ray of light definitely has bent here. It's not that it is going straight. Ray of light has bent here. Okay. Then ray of light is going like this, parallel to this. Again, this is perpendicular. Okay. Right. This is the wave front. Are you understanding this? Yes. So this is like the incident ray, and this is like the emergent ray. But now you call this as wave front. This is incident wave front, which is incident wave front, these perpendicular lines. And these are emergent wave front. Emergent wave front. Are you understanding this? So this is how the wave front will turn. It will turn like this. Clear? That's how prism will be. Then let us check now lenses. Let us go to lenses and check lenses. Now see lenses. Take example convex lens. So in convex lens, let us say that this ray of light is coming like this. Bending we will show afterward, but let us show the wave front. Again, parallel wave means it is plane wave front. This is incident wave front. Okay. Now here focus on this wave front, which had the middle part has touched it, but these parts have not yet touched it. So let us call ABC. The middle part has touched it, so when the wave will reach here B, this is traveling again more time. More in the time it will travel faster. So this point A will come here as C dash. This point B comes here B dash, and point C will be coming again here as C dash. Okay. So now this wave front has to bend like this. So you will be seeing the wave front will bend like this slowly, 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 and it become a point. So that's how the ray will look like. Now you can draw the ray diagram. Ray diagram may look like this now. This is what it is now. Parallel line meet at the focus. So this is the focus. This is the focus. Okay. So that's how wavefront. So wavefront, which was plane wavefront, has become a spherical wavefront now. You understanding this? This is how prism behave. What about concave? Concave also see. Look at concave. Let us look at concave. So take the rays. Rays, let us say parallel rays are coming like this. Afterwards, we will show how it is. We already know it is diverging, but let us show the wavefront. Plane wavefront. Let us draw plane wavefront. Now see here, I am taking at this point A, this point B, this point C. Note here A and C has already touched the surface, but the middle point has yet not touched it. So A will be traveling here in more denser medium, and B, C will also travel. C means the waves coming from C will travel in more denser. So it will take more time. Means time it will take, some time it will take. So that means wave from here to here C it will reach, here C dash, from A to A dash it will reach. By the time waves reach from A to A dash, and by the time waves reach from C to C dash, wave from B will also reach somewhere B dash, but B dash will come here. Why? Because it is traveling more time in rarer medium, so it will travel more distance. Because it is traveling faster, because some of the time it is traveling in rarer medium in air, right? That's why it is travels. So now the wave front which you have to draw, wave front if you have to show, you have to show wave front like this, like this, like this. Like this you have to show. That means if I show now ray I have to show like this. Ray I have to show like a diverging ray. That's why we know already diverging ray happens. But so they are not meeting. So where is the wave front? Where is the wave front from where they are coming out? So if you show by dotted wave front, it may look like it is coming from some point, right? Like this. So it looks like that it is coming from some point. When you extend them like this, right? When you extend them like this, it will look like it's coming. That's the focus for this concave lens, right? That's how it behaves. So lenses are over, prism are over, right? Then what? Then mirrors will take concave and convex mirror in the same diagram. That we have to take concave and convex. Concave mirror you take, concave mirror. Take parallel rays only. We are taking parallel or plane wave front. We are taking. Okay. So take plane wave front coming here like this. Means this is the ray. This is the ray it is coming. But wave front we need to draw perpendicular. So draw these perpendicular wave fronts. Now this is perpendicular we know. So these are incident wave front. Incident. Now here also note these points on this. Points A, point B, point C. Now what happens at A, reflection has already happened, now it is happening. Here also C, reflection happened, but B right now waves have not reached from B to the mirror, right? Because there is a gap here. So it will take some time to reach from B to B dash, let us say. By the time wave will reach from B to B dash, already reflection from A and C will happen. Already reflection from A and C will happen. So if reflection will already happen, that means what? This point will move ahead somewhere. We don't know, but it will move somewhere here. Ahead it does. And from C also it will move ahead. C does. Now you try to join the wave fronts. I will use different colors. To join A dash, B dash, C dash, we need to do like this. Okay. So like this it will happen gradually. Its radius will decrease. It will be coming from a point. That point is what is the focus here. So if I draw the ray will be going, ray diagram if I use, so it will be converging here. Right, ray diagram. So that's how focus happens for a concave mirror. That's how the parallel rays meet at the focus. Okay, that's what it is happening. Similarly, so that means what? These after hitting these rays becomes spherical, means wavefront becomes spherical, and they are meeting at this point. Then similarly, if you take convex mirror like this, convex mirror like this, if you take, and you take again, you have to see that these are the rays. This is the ray of light, and let me draw the incident wavefront. This wavefront I will draw a little bit more clearly. So this wavefront A, B, C. So A has not yet touched, but B have already touched the mirror, so it will reflect first. C has also not touched. C will take, so A and C will take some time to hit the mirror, but B has already hit it. So wave will produce from point B definitely. Wave will reflect, and so by the time Wave go from point A to this middle point A dash, and by the time C will go to C dash, it will already reflect. So B will come somewhere here as B dash. Okay, like this. Then try to make this rays. Um, Trace try to make also with a different wavefront. Try to connect A dash, B dash, C dash. So like this, I'm connecting. When it is reflecting means it is going this side, right? Reflecting means it is going this side like this. It will keep on increasing. So then what happens that it is going to look like a diverging rays. So rays will be going like this way, like this way. It is diverging. So when you stand inside, it will look like we were meeting it. So this is the focus. But if I have to show through wavefront, I can show dotted wavefront because waves are not going inside. So this is like a virtual wavefront. Like this. Okay. So that's the point where they appears to meet. So this is the focus. Right. So concave, convex, everything we can explain using this idea. Very important. Yes, yes. You may leave, Sam. You may no problem. You may leave it. Okay. I will keep continue the recording of this. Right? Fine. Okay. Yeah, yeah. I understand. Understand. That's why today nobody is there, and I when I started, nobody was also there. I just started because I want to keep on record of this. You may watch it afterwards also. Right? No, no problem. Don't take tension and don't rush. You can join anytime. Anything is there, you can always watch it afterwards. Okay. No need to take any pressure. Okay. So then we'll see next class. Mm, 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 mm. Very lengthy paper. Mm, mm, mm. It will be better. See, once what I will try to do, if you send me the paper, now I can discuss that paper also and some short tricks to solve those questions. So, like that, the paper also I can discuss, and this paper also I can discuss. Okay. So, if I can discuss, it will be better. Mm, 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 very, very lengthy it was. Understand. Okay, no worry. If it is lengthy or difficult, it is for everyone, right? So it is not only for your side, but practice will be needed from your side, right? So try to do more practice of problems, more like that. Well, generally they may not be very lengthy paper. Sometime only it may happen, but it is for everyone, right? Some management we have to do in that case, right? Cumulative? No, no, I don't know. It's cumulative. They have not told anything like that. Let's say still not, they have not communicated anything. So we'll see that. Okay, don't worry. Right now, current topics to focus, and then afterwards. Okay, then. Yeah. Okay, so uh, that's how it is working. All the how the waves are interacting. You may leave, Sam. Okay. So I will continue recording. Yeah. No, no, no. You may leave. You are feeling tired now. You may leave it. Okay, because you can watch it later also. Because if I don't finish now, then the problem is that it will extend and I will not be able to finish the syllabus. If I not finish this syllabus, then you will not be able to prepare fully, right? Uh, okay, okay, fine. So that's how means I can do it. So this is the interaction of wave 10. This now we'll discuss about the reflection of light waves. How light waves reflect. So let us consider a plane mirror where light wave is incident here on this surface. In NCRT also this explanation is given. Let us consider a ray of light like this parallel ray of light. Let us consider that parallel ray of light, and let us draw the wave front. So many wave fronts we can draw. Let us draw this wave front. So wave fronts are perpendicular to the ray. So this wave front is representing incident wave front. Okay. Now light ray has hit at two important points. Let us say this is point A. AB let us consider as the incident wave front, and C is a point where light has to reach. Okay. So by the time A and B will reach here, let us call this as B dash. By the time wave will reach from B to B dash, A will already start producing waves because it is now getting reflected. B will take some time to reach here. Waves will take some time to reach at this point, and then reflection will happen, right? So it will start reflecting itself. But let us show the angles here. What are the angles here? So I will draw a normal here. So this is the angle of incidence, and reflection don't know, but definitely ray will go in some direction. Okay, which direction it will go, we do not know, but let us consider that the ray is going to come from here. Let us first draw the ray diagram. Then we can think of drawing the exact diagram. So let's say ray goes like this. Reflected ray. Let us show that. So here also if I draw normal, so here now I can show that this is the reflected ray. This is the reflected ray. This is the incidence angle, right? So now I need to draw that point A dash. Where should I draw that? That carefully we need to draw. So by the time waves come from B to B dash, A gets reflected and it may come somewhere here. Somewhere here it can come. Let us say this point is B dash. B dash. Okay. So A, B, B dash, this is one triangle, and also we need to now make another. So wavefront, how do we represent wavefront now? This wavefront I will try to represent by um, joining this point B dash and A dash. Okay, B dash and A dash are this point, and this point B dash, B dash. They are two different points that we need to clearly see in this diagram. So this triangle is perpendicular and this is perpendicular, that we have to see. Okay, I will separately show this diagram. So this is A dash, B dash. They are perpendicular. Similarly here, they are also perpendicular. Okay, A, B, C. Okay. So by the time ray has come from B to B dash, this distance is equal to speed into time. And light is traveling from A to A dash in the same time. So this distance is also speed into time. So now if you take this triangle, these two triangles becomes congruent because AB dash is common. These angles are 90 degree and these A dash, AB dash are equal. So this triangle ABB dash ABB dash become congruent to triangle AA dash B dash. So congruent means corresponding parts are going to be equal here. So note that here this angle, which angle is I? I is the angle between this and this. So angle between this and this. So on this perpendicular angle between two lines is angle between their normals. So if you see vertical, perpendicular to vertical is horizontal, AB dash. And if you see this incident ray, perpendicular to this incidence is A dash. No, AB is perpendicular to incident ray. So AB and A dash, they are going to make the same angle I. That is what we have to know. AB dash, this angle is going to be same angle I. Similarly, what is R? R is angle between vertical and this reflected ray. So on vertical, this horizontal is perpendicular. On reflected ray, this this reflected in wavefront is perpendicular A dash. So A dash and this is going to make same angle R. So A dash, sorry, AB dash, this will make same angle R. So we know that because these two triangles are congruent, so corresponding parts are going to be equal, right? So this part A dash B and AB dash. So AB dash is equal in both, right? A dash B dash is making R and here AB is making I. So that angle I becomes equal to angle R. This happens by CP and this is the law of reflection. Law of reflection. So law of reflection can be easily proved from here by taking this idea of wavefront. Okay, using wavefront, law of reflection can be proved. Now, similarly, what is law of refraction? Law of refraction can also be proved using that law of refraction or refraction of light. Refraction of light. So if you consider refraction means you have to take ray of light going from one medium to another medium. So consider this is first medium and second medium. Consider carefully here so that diagram may look proper. I am just interested to show diagram properly. So this is the incident wave has come. Wavefront I will highlight. This is the incident wavefront. Okay, this is incident wavefront and this point, let us represent this point as A, this point as B. Now here what happens, by the time B will reach here to B dash, B will reach, because wave will reach from B to B dash, by that time A will start giving its own wavefront. Okay, so wavefront, of course, this point behaves like a sphere, right? It will produce a spherical wavefront. But let me first draw the ray so that I can clearly draw. Let us consider this is a denser medium. So normal, where is the normal? Draw normal. Draw normal. Okay. Let us consider it is going into denser medium. So ray will bend towards normal. So like this, you draw towards normal. You draw. Okay. Now I will draw the wavefront. Okay. Let me draw the wavefront. So this point will behave like a spherical wavefront. So by the time light will come from here to here, it will emit some spherical wavefront like this. Okay. That means this point A will reach here as A dash. It will reach here by the time B reaches to B dash. Now let us join this wavefront, reflected wavefront. So this is how the reflected wavefront will look like. They are perpendicular to this. Okay. Refracted wavefront are perpendicular to this refracted front. Okay, that's how the wavefront comes. Now we need to prove Snell's law here. So to prove Snell's law here, we will now consider this triangle. Note that this is perpendicular, and let us consider this angle of incidence. This is angle of refraction. Okay, so angle between this and this perpendicular and this perpendicular. So this is angle I again, right? And what is angle R? So perpendicular to this, perpendicular to this. This is angle R. So now you take these two triangles here again. Take and study these two triangles. So one triangle is this A P B dash, right? And in this is I, and same way here in this side, this triangle is there, this triangle here, this is perpendicular, this is perpendicular, this is A dash, okay? And this angle is R. Now let us look at these two triangles. They are going to be not congruent but similar. Why? Because let's try to understand B to B dash. Wave will travel B to B dash in some time. Sometime. That means here speed of wave is v1 and here speed of wave is v2. So speed into time v1 into t, and here to here v2 into t, right? So these two sides can be proportional. How can be proportional? Okay, let us calculate sine I in this triangle. Calculate sine I. Sine I is perpendicular by hypotenuse, which is v1 t divided by hypotenuse. Hypotenuse is ab dash. Similarly, let us calculate sine r in this triangle. Sine r in this triangle will be, they may not be similar, but let us calculate sine I, sine r. Sine r, let us calculate. So sine r is perpendicular v2t by hypotenuse is same a beta. Now let us take the ratio of sine I by sine r. So sine I by sine r ratio, when I take v1t, tt will get cancelled, impedance will get cancelled, you will get ratio v1 by v2, and speed is equal to c by n1, and this is c by n2. So that gives us the ratio of n2 by n1. That is how are we getting Snell's law. Snell's law now we are getting, right? Because n1 sine I is equal to n2 sine I. That is the proof of Snell's law. Snell's law is proved. So the law of reflection we have proved. Snell's law. Okay, done. So today we have covered a major topic in this chapter. So let us wind it now, and then we will be covering more in the next class tomorrow, hopefully. Yes, right, sir? So let us wind up this. We'll meet in the next class. Okay, bye. Good night. Yeah.